So this is where we left last time. So you have functional for the, we are doing the analysis of a transmission line, wave propagation along a transmission line which is open circuited, and you're giving a source voltage to the transmission line. So the functional expression is of this form. So now the approximate expression for potential is expressed in this form: alpha L BL plus alpha L here means left, R here means right. That's why we have put it L and R. So looking at this diagram here, this is the left and this is the right. So we have a subdomain basis, subdomain interval. We have a small interval from ZL to ZR. We want to find the approximate expression for the potential inside this ZL to ZR. So it is expressed as alpha L BL plus alpha R BR. And alpha L and alpha R are line functions. So line functions, one with positive slope and one with negative slopes. So this is the expression for B. If we substitute it here, then this is what we're getting. So B, I have replaced it by alpha L BL plus alpha R BR. Here we also have another expression for B, alpha L BL plus alpha L alpha R BR. So same expression, I've just replaced the approximate expression for the potential over the element line segment as alpha L BL plus alpha R BR. So as usual, we actually want to express this functional in the matrix form so that we can use linear algebra to solve it. So matrix representation here, you can see this whole expression would be replaced by matrix A. Then this whole expression here would be replaced by matrix B. So that's how we replace it. So A matrix will replace this term here, B matrix will replace this term here. What is A matrix and B matrix? We'll try to calculate so that we can write the functional in a matrix form like this. So here you are doing differentiation d by dz of alpha L BL plus alpha R BR, and you also have a square here. Similarly, you have alpha L BL plus alpha R BR whole square here. So what should A and B look like? So A and B should look something like the components of the Aij should be of the expression integration going from ZL to ZR, d alpha I divided by dz, d alpha j divided by dz here. So basically of the square term, you should have two of this differentiation, d alpha I by dz, d alpha z by dz. When you are having Aij, this will be alpha I, this will be alpha j. Similarly, Bij would be integration ZL to ZR, alpha I, alpha j, dz. So here your I and J actually can take either L or R. L is left and R is right. And as you know that interpolation functions or the what is that? Step function. Step function property alpha L plus alpha R is equal to 1. You can also see it from this diagram here. This diagram shows that this alpha L is having a value of 1 here, and this alpha R is having a value of 1 here. You sum them up, it will be 1 everywhere. So when you sum alpha L plus alpha R, it will be always 1 here. So using that property, we can actually find a relation between alpha L and alpha R. Alpha L plus alpha R is 1. So you can write this BE is alpha L BL plus alpha R BR. We can just express alpha L also in terms of alpha R is basically 1 minus alpha R BL plus alpha R BR. So we can find out this derivative with respect to dz for alpha I and alpha j. For example, if I want to find the derivative with respect to alpha R is a line with a positive slope z minus zr divided by, this is the line segment length, which is IC. IC is the total length of the solution, L divided by the total number of subsections. So that is, we have denoted it by IC. This is your step size. Alpha R is z minus zr by IC. So when I do partial derivative with respect to z, d by dz of alpha R, So I'll just simply get 1 by IC. Simple derivation here. dz will simply become IC d alpha. Once I have alpha, I can also find out the alpha I by dz. The alpha I by dz will be simply, you just replace this alpha AL. If you want to find the d by dz of alpha L, is just replace it 1 minus alpha R. So in that case, it will become minus 1 by IC. So we have all the derivatives with respect to alpha I and alpha J. We can substitute it here. So ALR, let's say if I want to find ALR, then it will simply become, what is the expression? Expression I think I have given here. Expression is this here. This expression you have here, the alpha I by dz, the alpha z by dz into dz. What is dz? dz is IC d alpha. So dz I have replaced it by IC d alpha, d by d alpha 1 minus alpha, because we are considering alpha L here. The alpha by the alpha, the alpha by dz, the alpha by the alpha, the alpha by dz. So it will simply become 1 by IC with a positive sign. So when I have ALR, I have a negative sign, minus 1 by IC. If I have ARR or ALL, it will become 1 by IC. Let's say if I want to find BLR, then I will replace dz by IC d alpha, then alpha L will become minus alpha, then alpha R will become alpha. So you are doing integration from 0 to 1, this will simply become alpha minus alpha squared d alpha. So when you integrate it, it will become alpha squared by 2 minus alpha cubed by 3, and the limits are from 0 to 1. So when you find out BLR turns out to be HE by 6. Let's say if I want to find BRR or BLL, then this will become IC 1 minus alpha is not required because both of them are same. So alpha alpha d alpha, so alpha squared d alpha is alpha cubed by 3. So when you substitute the limits 0 to 1, BRR will become IC by 3. So BLR is IC by 6, BRR or BLL is IC by 3. So now you can write A matrix is 1 by IC, 1 minus 1, minus 1, 1. So you have seen that A11 is 1 by IC, A12 will become, let's say ALL would be 1 by IC, then ALR will be minus 1 with the negative sign. That's why we have this. Off diagonal terms will become negative, negative. Diagonal terms, ALL or ALR will become always 1, positive. So 1 by IC, 1 minus 1, minus 1, 1. B, you have seen that B will have, let's say, BLR or BLL or BRR would become IC by 3. One is IC by 6. Of diagonal terms is IC by 6. So if I take out IC by 6 common, then I have 1, 1 for the diagonal term, and diagonal term was IC by 3. So we'll have 2, 2 here. So IC by 6, 2, 1, 1, 2. I have the expression for A and B. I can write the matrix form of the functional. So that is how you express the functional. Then in the FEM, so you have some kind of numbering. One is local. I have just 3 segments here, subsegments here. LR, LR, left side, right side, left side, right side. So there should be a LR here. Okay, so and you can do local not numbering. Local not numbering, you can have 1, 2, 3, 4, 5, 6. So you can see that these local not numbers are disconnected. But in the actual solution, I want to have a connected system. All of them are interrelated. So I will have a global connected system. So in that numbering, I will have 1, 2, 3, 4. So in the local node numbering, I have 1, 2, 3, 4, 5, 6 because these are disconnected. segments, and in the global one I have 1, 2, 3, 4 because these are all connected. So I want to find a relation between this local node and global node. So that's how you do it. You first find the local coefficient matrix, then you find out the global coefficient matrix. Similar to that here, I have two kinds of numbering. One is local node numbering and global node numbering. I want to find a relation between these two. So you can easily do that. So basically in the local node numbering you have 1, 2, 3, 4, 5, 6. And the global node numbering you have 1, 2, 3, 4. So let's say B1 should be equal to B1. B1 of the local node should be equal to B1 of the global node. B2 and B3 of the local node numbering should be equal to B2 of the global node numbering. B4 and B5 of the local node numbering should be equal to B3 of the global node numbering, and B6 of the local node numbering should be equal to B4 of the global node numbering. So this is a relation. No? We can write this in a matrix form. B disconnected, it will have B1, B2, B3, B4, B5, B6. B connected will have only 1, 2, 3, 4. So B1, B2, B3, B4. What is the connection? What is the relation? This is given by this M matrix, M connection matrix. That matrix would be C. B1 should be equal to B1. So when you multiply this first row with this, you get B1. B2 should be equal to B2. That's okay. How about B3? B3 should also be equal to B2. So B3 from left hand side for the disconnected case should be also equal to B2 of the right hand side, which is a connected case. That's why you have 0, 1, 0 here, 0, 1, 0 here also. B4 and B5 is equal to B3 of the global node numbering. B4 and B5 of the local node numbering should be equal to B3 of the global node numbering. That's why you have 0, 0, 1, 0 here, 0, 0, 1, 0. When you multiply this, you get B3 here. When you multiply this, you get B3 here, which is equal to B4 and B5. B6 is equal to B4 of the global node numbering. B6 of the local node numbering is equal to B4 of the global node numbering. So this row, you multiply it, you are getting B4, left hand side, you have B6. So this connection matrix actually is showing some connection between the disconnected voltages and the connected voltages. So disconnected is for the local node numbering and connected is for the global node numbering. So this is a relation between the B disconnected and B connected, and we call this is M connection matrix. So yeah, so 1 and 1, 2, 3 should be equal to 2, 4, 5 should be equal to 3, and 6 should be equal to 4. This is the local node numbering, this is the global node numbering. And we also have this matrix representation of the functional, and this was like this. Matrix representation of the functional was BLBR 1 by LE A minus omega square C B BLBR. So when you multiply this, finally this is what you're getting. And this voltages you have considered is actually disconnected voltages. That is, in this particular example, it will be B1, B2, B3, B4, B5, B6. Okay, so in the very compact form, I can express this functional as B disconnected transpose C disconnected, then B disconnected. And what was the relation between disconnected voltage and the connected voltage? It was M connected, then B connected. So we will replace this B disconnected by M connected and B connected. And here is B disconnected transpose. Transpose actually, then you can write B connected transpose, M connected transpose. I'll replace this by the connected one. So finally, what you're getting is FEBE is equal to B transpose connected, then this whole thing here inside, we call this as connected coefficient matrix. We multiply with the B connected. So this whole thing here, even the disconnected coefficient matrix, when you multiply by transpose of connection matrix and pre-multiply by transpose of the connected matrix and post multiply by connected matrix, you get the C connected. This is the coefficient matrix of the connected or global system. So the expression for the global coefficient matrix, which is also called connected matrix here, will have two terms. One from the, see, this was the expression for FEBE. So what we have here is this. So here, if you look at the C disconnected is dependent on A and B. So, and if you want to find out the connected C connected matrix or the global coefficient matrix, I can find it out from the C disconnected or the local coefficient matrix by multiplying with the connection matrix. pre-multiplying with the transpose of the connection matrix and post-multiplying with the connection matrix. So here your C disconnected itself has two components, A and B. So two terms for the C connected, 1 by L M transpose connected A matrix, then M connection minus omega square CE M connected transpose B and M connected. So this is how you can find out the global quotient matrix. And this first term people usually call as the connection matrix 1 minus connection matrix 2, where connection matrix 1 is expressed like this, which is dependent on the A matrix. Connection matrix 2 is expressed like this, which is dependent on the B matrix. So let us try to find out the expression for the connection matrix. Connection matrix A matrix was 1 minus 1 minus 1 1 1 by IC, and you have the expression for the connection matrix. We have discussed that connection matrix transpose of that you multiply with the A matrix, then M connection matrix. So let me just go back to what was the connection matrix. Connection matrix was of this form here for this particular example. So finally, this connection matrix 1 would be of the form 1 by L IC. L from here, IC from here. Then finally, this is a tri-diagonal matrix with the diagonal elements first and last is 1. All other remaining elements are 2, 2 here. So similarly, C connection matrix 2 would be omega square C M transpose B M connection matrix. B matrix was IC by 6 to 1, 1, 2. We have found out that. And you know the connection matrix. When you multiply and find out what is the connection matrix 2, it will turn out to be omega square C from here, IC from here, divided by 6 from here. Then you get a tri-diagonal matrix here. 2 and 2 is for the first and last element. And all the off-diagonal elements are 1 and remaining diagonal elements are 4. So we have connection matrix 1, connection matrix 2. I can find out the global connection matrix. So finally, the expression for FBE would be B transpose global coefficient matrix B connected. So when you write this, it will have the general form of this from trigonal elements and off diagonal elements, below the diagonal elements and above the diagonal elements. This is a tri-diagonal matrix. I have expressed in a very general form. And you have B1, B2. See, basically what we have derived was for the global coefficient matrix. So let's say if there are n nodes, then this B matrix will have B1, B2 up to Bn. Again, B transpose. This is a B transpose, and this is a B matrix will have B1, B2 up to B capital N. B transpose would be a row of the form B1, B2 up to B capital N. And this connection matrix will be having general form like this, tri-diagonal, in the tri-diagonal matrix. So when you multiply this vector with this diagonal matrix and this vector here, then finally your expression of this form would be of this form here. And if I want to find see, what are we trying to find here? We're trying to find the voltage here, B1, B2 up to Bn here. But then the problem we have considered was finite element analysis of transmission line. In that, what we have is we have open circuited RL tends to infinity, load is here, the source you are providing is B naught here, at Z is equal to L. So at Z is equal to 0, you have an open circuited load, and at Z is equal to L, you have a source of voltage B naught. So in that case, this last term here, B capital N. No? So voltage for B capital N is prescribed. So that's what you need to understand. Bn is already known here because we know what is the voltage at Z is equal to N. This is equal to B naught. So when I do differentiation of partial derivative of the functional with respect to B1, B2 up to Bn minus 1, I will not do it for Bn because Bn is already known to us. Bn is prescribed. So when I do that, what I'm getting is something like this. So then you equate it to 0. you do the partial derivative of functional with respect to b1, b2 up to bn minus 1, and you equate it to 0. But then what is the last term? The last term is not 0, because look at this expression here. Last term would be Cn. This last term will not be 0, but minus Cn n minus 1 and Bn. So all other terms would be 0, because the last term Bn is not, Bn is prescribed and we know it, so we'll have. So from here you can solve all the values of B1, B2 up to Bn minus 1. That's how you do it. So let us go to the next one. Next one is basically we want to find out the solution of the Poisson's equations. So we have already done it for Laplace equation. We want to extend it for Poisson's equation. This is more complicated than Laplace equation. The first thing, the FM analysis example we have taken was for the Laplace equation. So now we want to extend it further to the Poisson's equation. Laplacian of potential is equal to, we want to derive the element governing equation. So in the Laplace equation, we were just interested in just finding BE is equal to summation I going from 1 to 3 BEI alpha I. That was the first example we have considered, two element mesh. So, but here in the right hand side also we have rho B here. So right hand side is no longer 0 here. So right hand side also will discretize it like this. Rho B is equal to summation I going from 1 to 3 rho EI alpha I. This is the only difference. This term was not existing for the Laplace equation. So now right hand side is no longer 0. So we'll also discretize the right hand side. Rho B is equal to summation I going from 1 to 3 rho EI alpha I xy. Alpha i's are the shape function. BI are B1, B2, B3 are the potential at the node 1, 2, and 3 of the triangular element E. Similarly, rho EI are rho E1, rho E2, rho E3 are the potential volume charge density at node 1, 2, and 3. This should be actually prescribed. This is already known to us. But we are interested in only finding BEI. Once we have that, we can find the solution. Let's go back to the Euler's equation and the functional. This is the most general form, Laplacian of phi plus k square phi is equal to g, and we'll have functional of the form I phi is equal to half double integration del phi square minus k square phi square to phi g ds. And our Poisson's equation, Euler equation is del square b is equal to rho b by epsilon. So we don't have this term here. This term would be there when we consider the wave equation. So del square b minus rho b by epsilon. So I transfer this epsilon to the, multiply this epsilon to the left hand side. What I have is epsilon del square b is equal to minus rho b, and transfer all this term to the right hand side. Be careful, just transfer all terms to the right hand side. So minus epsilon del square b minus rho b is equal to 0. So here, what we have here is negative here, so that's why 2 phi g. So ours would be minus 2 phi rho b. So minus 2 phi minus 2 phi rho b. Phi here is voltage here. So here is phi, here is voltage here. So
Hello, sir.
Oh, it seems I was disconnected due to internet issues.